Assalamu alaikum wa rahmatullahi wa barakatuh. Today we are going to start lecture number 3, in which we are going to discuss Prokon. Prokon is a famous software in which civil engineers are using for structural analysis and design. We are going to learn about the basic interface of the software, some examples, how to run basic fundamentals of engineering, basic structural analysis, and then basic design of concrete elements. Now going for the Prokon, this is the icon of the Prokon. If you can see here, Prokon is having certain tabs. Okay, where we have home, we have analysis. Now in analysis there are different options. So we have SOMO, that's a structural modeler, or the 3D modeler, frame, so frame analysis, plane stresses. So for example, if you want to analyze a bridge or a dam. Beam, this is analysis of a single span beam. So if you want to do the analysis of beams. Elastic analysis of a beam on elastic support, which is an example of plinth beam. Elastic support is considered, or the soil is considered to be an elastic support. Steel, doing the analysis and design, or doing the design mainly for different members. You can see that, for example, struts, and then a combination of stresses, crane beams, post girders, oblique girders, and then a lot of things as well in terms of connection for the moments, in terms of connection for the shear. We are not going to deal mainly with the steel design. We are going to deal mainly with the concrete design. Hopefully in other lectures we are going to cover the steel design. Now in concrete, if you can see, we have different options as well. We have CB, which is standing for continuous beam or slab, that can be used for a regular slab or a flat slab as well. A capitan, that's a post tension beam or a slab. And then we have a regular rectangular slab, analysis and design, rectangular column, circular column, general type of a column, a retaining wall design, base including both isolated and combined foundation, crack width for elements that requires to be checked for cracks, concrete section, design of a general concrete section, and then bunch and shear check. Timber and masonry is there as well. So if you want to do certain things related to timber design, related to masonry section design, related to masonry wall design as well. CAD and detailing, this is where the software is performing the detailing. General basic things as well are there. Pro section, where we are getting the properties of the section. And that's going to be the first example that we are going to deal with. And then wind simulator, or wind pressure analysis, a gutter size design, section database are there as well if you want to add another section, material if you want to add another material, geotechnical, slope analysis. All of them are related to slope stability. So we have rock stability as well, and then we have regular soil stability, and then other things which are related to bearing capacity of shallow foundation. How would you calculate the bearing capacity? And then we have shear strength of rocks, and then we have shear strength of rough joints in the rocks as well. Finally, we are having the pile bearing capacity. I don't think we are going to cover geotechnical in this particular video, maybe in the other videos, because analysis, properties or general fundamentals of engineering and then design of RC will require a lot of time. So hopefully we are going to cover it in further lectures. Now, mainly I have done booklet, a small booklet, in which it explains the basic examples of using Prokon. This was done previously to the students of the college, of the Higher College of Technology in 2019. A lot of things are there. We are going to solve the examples from here. We are going to illustrate them, and then I'll upload for you the what you call the handout as well. Now you can see in this particular document, the toolbar has been explained. Different illustrations are there. So what's the meaning of each one of them? Some examples from the software, and then we can see what is the function of the frame, or how we can use the frame as well. Plane stresses as well. So this is an arch bridge, and then beam, how to do the analysis of the beam, elastic foundation, or elastic beam, or beam on elastic support, and then continuous beam portion, and then post tension or capitan, general things like column retaining also. So basic idea about the things that I have already explained for you. Now the first illustration that we are going to do is how to find the section properties. Okay, we have a certain section, we need to calculate the properties: centroid, moment of inertia of x, moment of inertia of y, centroid in terms of x, centroid in terms of y. So basically we want to find the section properties for this I section. Now going for Prokon, to find the properties of any section, we normally go to general. In general there is property sections, so we go for the properties. So a pop-up window will come for us, and then we have different options, plus and minus mainly we are using. So plus is the positive direction, means right is going positive, left is going negative, and then above is going positive, downwards is going negative as well. Okay, so we are going to use the regular system, which is plus. Now to understand how to play with this particular software, we need to start with a basic point. So let's assume that we are starting from this particular point, which is my, let's say, my 0 and 0. Okay. Now I want to move and specify the second point, which is this particular point. So this is my first point, this is my second point. Now if this is 0, then I have moved, in order to go for the second point, I have moved 20 in the x direction. So it's positive 20 since I went to the right side. So 0, and then I went in the right direction by 20. So at the beginning, what I need to do, I need to go right here in the second tab. The first tab is going to go for the convention. So I'm just writing that in x I'm having it to be 20, then clicking enter. So the first line will be drawn for me. Now going for this second point, so I'm here right now. Now I need to go up by the value of 10. Up is in the direction of y, what you call horizontal is x, vertical is y. So we are going from this point to this point, and in the vertical direction, going up by the value of 10. So it's going to be plus 10. So I'll come to the software, and then I'll tell that in terms of X I don't require anything, in terms of Y I need to put plus 10 or 10. Now do not worry about this shape which has been drawn. This is just a generated shape. It will be updated automatically for you. Now going once again here, we have reached here. I need to go to this particular point, so I need to go to the left side by the value of 5. So once again I need to go in X by the value of 5, but it goes to the left side, so it's negative 5. So we're going to have it as negative 5. Now after negative 5, we are going up by the value of 120, which is in the vertical. So we are going to have 120 in the Y direction. Now after finishing the 120, we are here. So we need to go for the X direction by the value of 15. So 15 in the X direction. And then after the 15 in the X direction, we need to go up by a certain value which has not been mentioned. So if it's not mentioned, then we can take it as 10. So going from here to here in the vertical direction or Y direction by the value of 10. Since it's going up, so it's going to go positive 10. Now we are in this particular point, we need to go to the left side, which is representing X. So we are going in the left direction of X, that's minus 40 to reach to this particular point. So this is going to be minus 40 in X. And then after minus 40 we have reached here. Now we need to go in the vertical direction or Y direction, downward side of Y by the value of 10 once again. So we are going for 10, so it's minus 10 since we are going down. After that we are going from this point to this point. Okay, so we're going in the X direction, so positive X, so that's going to be 15. After the 15 we are going in the Y direction, we are going down, so that's negative 1. So this is going to be minus 120. Now you need to take into account that in terms of X, if we are going right, then it's positive. In terms of left, we are going negative. In terms of Y, upward is positive, downward is negative. This is what we are trying to do. Okay. Now we have reached to minus 120. So minus 120 we have reached here. Now once again I need to go in the X direction, but this is the left side, so it's going to be minus 5. So in the X direction this is minus 5. And then you can see I don't need to go and connect the remaining thing as it's already connected here. Now you can go and see that I have 40 here. Again I have 140 as a total length. Okay, so 120 plus 10 and 10. Now in this example I think I have taken the top portion to be 15. Anyhow, you can check and try. All the examples which are there in the handout are solved, so you can go and follow step by step. Okay. Now after we have drawn this one, we require to get the properties, so we can go for properties here, and we can see that the centroid will be located at the distance of 77.22. We have different things which are there: IXX, IYY, AAN. Z values, a lot of parameters are there. We just need to use whatever is relevant for us. As well, it will show you like the shear stresses, the torsion, shear stresses of X, shear stresses of Y, the torsions where it will be located, and you can see mainly the stresses will be maximum on the joints wherever there is a difference in terms of the area, okay, or there is irregular joints, like the connection between here and this particular portion. And then the good thing as well, you can get the calculation sheet So all the required things you can get them from here with the figures. You can click on output setting as well, and you can choose whatever things you require. So for example, I don't require the values, I require only the sketches. So I'll just have them. Okay, so it will only show me whatever I want. Okay. Now if I want, for example, the sketches, okay, it will show me whatever is relevant as well. Okay. Um, this can be taken as printed as from print now. You can save it as PDF, and you can further do whatever is required from you. Okay. Now that's the first example where we have used Prokon, to get for us the properties of any sheet. The only thing that I need to get the coordinates of that particular sheet, and then I'll be able to find the properties for the sheet. Now going for the second example. In the second example, we are trying to go to analyze a single span beam with different loadings, taking into account the self weight of the member as well. So the question says for you, the example says for you that we need to find the shear force and bending moment for an I section of a certain particular section, and the loading is shown in this particular section. So what we need to do, we need to go to Prokon, we need to go to analysis, and then from analysis we need to go to beam, because here it represents for you a single span beam. So we click on a single span beam option. Now we have got this particular window. We need to input certain things right there. So according to the question, we have the total length is 6 meters. So we return back to the software saying that it's going to be 6 meters. So it has drawn for you that this is 6 meters. Now, is it fixed from the left? What type of support? Is it fixed, pinned, or free? Okay, the same thing for the right support. So going for the left support, and we can see that this is going to be pinned from the left support and pinned from the right support. Okay, pinned and then pinned. Now pinned is including both hinge and roller. Okay, now you can see I need to calculate I and E, otherwise I need to select the section, and then the section will be checked automatically. So going for the section, we have steel, concrete, and then timber. So we're going for steel. Different sections are there which are available already. Now we can go for an I section. Which section has been given for us? It's 203 into 133 into 25. So we need to go for 203, 133 into 25. Click on it, and you can see that the I has been calculated directly as per the section. Now E value. You can input it in the material, or you can use whatever is given in the software. Now the software has given you two values. One is 206 to the power of 6. That's Young's modulus of steel, and then approximate Young's modulus of concrete is 25 to the power of 6. Now choosing 2000 or 206 to the power of 6. Now you will see that this particular value has been given here automatically, which is 0.246, and 0.246 represents the self weight of this particular section in terms of kilonewton per meter. So the self weight has been already induced inside the calculation. I don't need to go and calculate it once again. Now going to check the other loads. We have 10 and we have another 10, so 2-point loads, each one of them is 10, and then we have a moment, a clockwise moment of 15. So first we'll go and define the 10. So we can see here that we have W left and W right. This is representing the UDL. So for example, if I go and put, for example, 5 here and then another 5 here, you can see now the total loading became to be 5.2. That's 5 plus 0.246 in both sides. Now if I have written that this is 0, for example, and then the right side is 5, you can see that this is going to be 0.246 representing the L3, and this particular value is going to be the 5 on the right side plus the 0.256. So W left and W right are related to distributed loads. Now we don't have a distributed load. The only distributed load is the self weight, and it has been calculated automatically. So we need to remove the 0 and 5, and then clicking enter to update whatever we have done. And then we have A and B as well. These A and B are related to the distributed load if you want it from a certain portion to a certain portion. Like for example, let's say that they want 3 meters and then another 3 meters, but they want it to be from the left support. They want it to be of 2 meters, 2 meters from the left support, and then I want it to be of 3 meter load. So what you can see here, you can see that A is representing the distance from the support. So A is representing the distance from the support, and then B is representing the length of the load. So we have said that the distance from the support is 2, while the distance for the load is going to be, or the distance where the load is applied, is 3. Now we don't have that one as well. We are just explaining the things. Now we have P, which is representing a point load. A, where is it exactly from the left support, and then M, where is it exactly from the left support. Okay, so now what we need to do, we need to go to P. Now in this particular example, you can see P is going downwards, so it means that the direction of the load is going to be positive for the bottom, okay, or downwards direction. The sign convention is downwards positive. So I'll just apply, I have it as 10 kilonewton, so I'll just go and put it as 10 kilonewton, and then I have it at the distance of 2 meter. I have it at the distance of 2 meter from the left support, so just writing that it's going to be 2 meters. So I have a downwards force of 10 kilonewton at a distance of 2 meters from the left support. And then once again I have another one, which is going to be 10, which is the distance of 4 meters. Okay, so we have another load which is 10 at a distance of 4 meters. Now going for the moment, now we need to go and check the direction of moment. You can see here the direction of moment is going anti-clockwise. So anti-clockwise is positive. Now our moment is clockwise, so that's going to be negative according to the sign convention given by the Prokon. So it's going to be minus 15. Once again, the sign convention here given is going to be anti-clockwise or counterclockwise, positive. So I have mine to be clockwise. That's going to be the opposite side, which is negative. So negative 15 at a distance of how much from the left support? So we have the total length, that's 6 meters. So we can see now a clockwise moment of 15 has been applied at a distance of 6 meters from the left support. Okay. Now after we have finished all of these things, what we can do, we can start analyzing, and then we can see that this is a deflection, and you can scroll your or you can move your mouse to check what's the deflection according to the section given. And then the shear force, you can see that it's shear force is increasing here, or it's starting to have a high value because of the reaction. Now going down slightly because of the self weight of the member, going down because of the point load, decreasing slightly because of the self weight once again, going down because of the point load, and then slightly decreasing because of the self weight, and then going to the 0 point because of the reaction. Now for the bending moments, once again you can see that it started by 0. It's supposed to be going to 0 because it's a pin support, but nevertheless we have a bending moment here. So this is going to be having, this point is going to have a minus 15 bending moment. So this is going to go 0 bending moment in this point because of the point load, and then another point load here, and then you can see it's going up. So this is an analysis of a single beam. The software is very easy in terms of using it. You can play and have different combination of loads, and once again you can get your calculation sheet where we can show everything that we require, and then we can print now, so it can be printed in terms of PDF. Okay. Now going to example number 3. Now in example number 3 we are going to analyze and design a slab, and the question says we need to analyze and design a restrained internal slab of 5 meter length and 4 meter width. The slab is supported by beams from all sides, and the floor finishes and live loads are having 1 and 1.5, and then grades of concrete are 30 and 460 for concrete and steel, and then it's designed using BS code or BS 8110. Now, certain things we need to understand before going to apply the parameters or the inputs which are there in the example. We need to understand mainly what's the meaning of restrained and what's the meaning of internal. Now, restrained is happening whenever our slab is connected properly with its support. So in case of a beam, the slab and the beam are connected properly. Like for example, if we are having regular construction of concrete, normally we have monolithic construction where the slabs and the beams are bored together, so they are properly connected with each other. Now the other type of connection in terms of two-way slabs, since this is a two-way already, because the longer direction or the longer dimension, which is 5, divided by the shorter dimension, that's 4, is going to be lesser or equal than 2. So the other supporting, or the other support, is a simple support, and that can be represented by having a concrete slab supported by steel beam. Now, if there are no connections between, if there is no connection between these two elements, then we can consider the supporting system to be simple, unless we are having some kind of drilling in such a way that this particular, or we're drilling some kind of steel inside the concrete, from the concrete slab to the steel beam, or some kind of joint between them. In that case, it will be only considered as constraint or restraint. Now going for the Prokon, and then we'll learn what's the meaning of internal over there as well. Now in concrete tab we have different options. Mainly we are going for a slab. Now we can see a lot of things are there. We need to understand them so we can analyze and design our particular slab. Now the first thing, we need to ensure that the design code is whatever you want. So in our case, the design code is going to be BS8110. Now we need to input certain things. LX, which is a shorter direction, so the shorter direction in our case is 4. meter, and then the longer direction is 5 meter. Now the slab depth, let's return back to the question. Now the slab depth has not been given. The slab depth has not been given. So let's say, let's assume that the slab depth is going to be around 150 mm. Okay, so slab depth, it can be calculated as well using the equations given by your code, but we can assume it here as 150. This is the total depth of the slab. Now effective depth of the slab, so we need to remove, let's say that we have a cover of 20 and then we have a diameter of 10, so that's going to be 150 minus 20 minus 5, that's going to be 125. And then in terms of y direction, or in terms of effective depth in terms of y, then this is going to be, once again, it's going to be as 125 minus the diameter of x, which is 10, so that's going to be 150. Now to illustrate that thing, if dx and dy are not that clear for you, let me try to illustrate it. So what we can see here, what we can see in this particular example, assuming that this is a slab, this is the shorter direction, that's a longer direction, so this is Lx, this is Ly. Now at the beginning we are going to have the bottom reinforcement, which is parallel to the shorter direction, so this is Lx, so the shorter direction reinforcement is going to be parallel to Lx, and then we have the longer dimension reinforcement, which is going to be parallel to the other side, which is the longer dimension. Now if we are looking at from the Lx direction or from Lx perspective, now we can see that we can only visualize one bar in terms of x, because the other bars are behind this particular bar, they cannot be seen. And then we can see the bars which are parallel to y. So once again, returning back, now we can see this is the reinforcement of x. We cannot see, if we are seeing from this particular perspective, we cannot see the other bars, we can see only the first one. While in terms of y, these are the black color ones, we can see all of them. Okay, so it's represented in this particular shape. Now if we are zooming in a certain portion, taking this particular portion out, now the total depth, which we represented as 150, is from the total, from the top fiber to the bottom fiber, and then dy is from the top fiber till the center of gravity of the, or till the centroid of the y bar, and then dx is from the top till the center of x direction reinforcement. Now let's assume that the total depth is 150, and we say that the diameter is 10, and then the cover is 20. So in this case, dx is equal to the total depth, which is 150, minus, we need to reduce the cover, so that's 20, so 130, minus half of the bar, because it's at the center, dx is at the center of the bar, so that's 10 divided by 2, that's 5. So 150, the total depth, minus the cover, that's 20, minus 5, that is half of the bar, so it's going to be 125. Now in terms of y, it's going to be cover once again, minus the full of x minus half of y, so 150 minus the cover of 20, so that's 130, minus the full depth of the full diameter of x, that's 10. So 130 minus 10 is 120. 120 minus half of the bar, that's 10. 10 divided by 2 is 5. So 130, 150 minus 20 minus 10 minus 5. So 150 minus 20 is 130, 130 minus 10 is going to be 120, 120 minus 5 is going to be 150. Or what we can say, it's 125, that's dx minus the diameter of the bar. So 125 minus 10, that's 150. Now returning back once again to Prokon, you can see that we have given as 150, 125, and then 115. Poisson's ratio according to the BS code is 0.2. Grade of concrete according to the problem we had is C30. Now, if you are having the demo type, you will be limited to use certain grades only. You cannot use further grades. So FCU, or grade of concrete, is 30. Grade of steel is 460. Density of concrete is going to be 24 according to the code, and then self weight is going to be 1.4. Now you can see before entering of it, before pressing here, you can see that the total loading right now is 0. Now if we click on 1.4, you can visualize that the total loading became 5.04, and this 5.04 is representing the self weight. Now the self weight of the slab is calculated as 24 multiplied by the depth of the slab. So our depth is 0.15, 3.6. Still we didn't get the 5.04, but you need to keep in mind that this is a factored value, where the factor of safety for the self weight according to the BS code is 1.4. So we need to multiply it further by 1.4, and we can get exactly the same value that we are getting. Now going for the other things that we need to understand, we have displacements and we have rotation. Displacements is related to the support which is available in that particular edge. So you can see that we have a beam on the top edge, bottom edge, and then the two sides. If we remove one of the tick, you can see that there is no beam at that particular portion. So displacement is related to the supporting edge of that particular portion. So it says for us in the question that it has beams from all sides, and then we need to understand what's the meaning of rotation. Now in rotation, now you can see that this slab is discontinuous from all the sides, means it has a bending moment of 0 at the end. Okay, now if we allow rotation or moment, it means that this particular slab in that particular portion is going to be continuous rather than discontinuous. So if we take the rotation here, you can see that there is a continuity because of the rotation or because of the moment. There is a continuity. Now when we say internal means the slab is in the middle of the structure. It means that it has surrounding slab from all directions. So we are going to tick all the sides. So we are going to have continuation from all the sides. Now after this we are going to input the loads and then visualize the results. Now going back, let me just close this one. Going for the example once again. Now we can see that the finishes are 1 and then the live load is 1.5. Okay, now returning back. Now load combination number 1, we'll just write load combination. LC is representing load combination. I have two factor of safety which is for the live, which is 1.6, and then 1.4 for the dead load. Now we have different options. One is UDL, another one is factored point loads. So if you are having point loads, like for example a tank, or line loads, if you are having a wall, for example, you can specify. Now you need to keep in mind that all the loads are non-factored. They will be multiplied by the factor of safety. So UDL, in our case, the UDL is 1 for the finishes, which is the dead load, and then live load or imposed load to be 1.5. So we're having 1 for the finishes and 1.5 for the live. And you can see automatically this will be changing according to whatever we have input as a loading. And then we can go and get the moment. Now for the moments, we have said, now since it's continuous from all the sides, of course you will be having moments from the top in all the directions. Okay, now what we need to understand, we need to understand the behavior of that particular slab, and on what basis it showed me the bending moment diagram. Now this can be illustrated here. If you can go and see, this particular slab is continuous from two sides, and it's discontinuous from the right side and from the top side. Now if we go and draw the bending moment diagram, since it's discontinuous from this side, the bending moment is equal to 0. So there is no bending moment here. While it's continuous from this particular direction, so there is a bending moment. Now in the other side, once again, if we take a line here, you can see that it's discontinuous here, which is representing a 0, and then you can see that this particular portion is having a continuation. That's why we are having a bending moment. So whenever there is a continuation, bending moment is going to be there. So the top moment is available here because this portion is continuous, and then bending moment is available here because this portion is continuous. Now going back to the Prokon. Now in terms of x, this is my shorter direction, okay, and this is my longer direction. So this is horizontal, this is vertical, and you can see the bending moment here is having a value, and then here once again is having a value, and in this particular portion there is no value because it's representing the bottom bending moment. Going back once again here, you can see in this particular portion, this is representing the bottom, so the bending moment in this particular portion will be representing only the bottom, and in this particular portion it's going to be representing the top. Okay, so once again returning back here, you can see that because it's continuous from both sides, so it's bending moment here going up, bending moment going up, and then this is going to go down. The same way on the other side, what we can see that once again it's continuous on this side, continuous from this side, so it's going to be having a top bending moment in both sides, and then remaining side is going to be bottom. Now to understand a little bit, let us try to have a different approach. Let us try to remove the top, and then let us remove the bottom one. So it's discontinuous from this side, discontinuous from this side. Going for the moments, so we can understand. Now, what we can visualize. We can visualize this in terms of horizontal direction. This is my horizontal direction. There is a moment here, and there is a moment here. Now, in terms of the top, there is no continuation. So no moments are represented in this particular portion. Whatever you are seeing right now is because of the columns. Okay. Now, if we go and apply, let's say no bending moment, no continuation at all, you can go and see that we don't have actually in this particular zones. In each zone, the only thing whatever we have is the column portion. That's a bending moment in the column portion because it's representing a flat slab system now, since there are no beams. So returning back to our question, where all the sides are having beams, um, and this is representing the bending moment. This is the deflection where it occurs at the center always, and then we have the reinforcement, how much reinforcement is to be supplied at each and every position. So at the top, in the top of X, the maximum bending moment or the maximum reinforcement is 175 approximately. In the center, the bottom, this is the top, this is the bottom. On the bottom, we are having around 87. So in the other direction, in the longer direction, 62, and then 151. Always the shorter direction are going to have the bigger moment and the bigger reinforcement as well. And then we can go for the bending schedule, and we can see we have different reinforcement. So you need to understand certain things here, so you can read this particular reinforcement or the schedule which is represented here, the bending schedule. Now uh, the line which is representing the total or the line which is cutting the slab fully is representing the bottom reinforcement, because we supply the bottom reinforcement on the entire slab, while the top is not going to be the same. So what we need to do, the first thing, we need to check the line which is cutting the slab fully. So we have one here, and then we have another one here. Okay, now this one, where it says for us, we are having 11, that's number of bars, so 11 bars. Y is representing the grade, that's 460, or T. 10 is the diameter that we have supplied. F is labeling, so the label is called, this line or this reinforcement is called F. The spacing is 400. B, what's the meaning of B? B means bottom, because this line is fully covering the slab. This is what we have said. 2, what does it mean? It means that we are talking about the Y direction. Okay, we are talking about Y direction. Now going for the other line which is covering the slab fully on the X direction or in the horizontal direction, we can see 13 number of bars, 10. Once again, labeling is different. Label is A, spacing is 400, and then B1. B1 is representing, B is representing bottom, 1 is representing X. Now the same thing for T. T is representing top, 1 is representing X, 2 is representing Y. Okay, so we have certain reinforcement in Y direction. Okay, and we have like T2 and then T2. This one and this one is representing X, and then we have this one Y, and then this one T1 and T1 is representing X. If it's not that clear, it might be clearer here somehow. This is the detailing and how it's shown. You can see that this is the reinforcement of X, and then after the reinforcement of X, we are going to have the reinforcement of Y, and then in the example that we have tried to solve, you can see that the bending moment in this particular one, the bending moment is available only on one side. It's not available in both sides. So this is X and this is Y. We are drawing the detailing only for X. Okay, so if this is my X direction, I can see that for X I have bottom portion, and then I have top portion. Top portion is only available in this particular left region. We don't have it on the right region. So in this case, what will happen? We can see the reinforcement is only available on the left side. So you can see that the reinforcement at the top is only available at the left side. and this is going to be the other side reinforcement. Okay, let us try to see if another example is there so you can understand a bit easier. Same thing here. Okay, so once again, this is Prokon. This is the design of the slab. We are going to stop here. Hopefully, in the next lectures, we are going to have, or the next portion of Prokon, we are going to continue other things uh, which are going to be analyzing and designing of a rectangular beam, and then we are going to have analysis and design of a continuous beam. We are going to have analysis of a concrete frame, and then circular column, rectangular column we can have as well, isolated foundation, and then we can have a combined foundation as well. Retaining wall will be having in the next lectures as well. Some exercises that you can try yourself. The last thing that I want to conclude in this particular lecture is to show you certain things which we can get in Prokon easily as well. If you remember, in robot structural analysis, we have done the library or the generator that can make our job a bit easier. So the same thing is available here. We can have in the analysis tab, we can have frame. Now in this particular frame, we can have different types of shapes, different types of structures that can be generated with inputting only certain parameters. So we don't require to go and model the whole thing. So now if we can go and check this particular thing, we can see that we have different things. Apologies for the resolution. The resolution of the laptop is a bit higher. Now you can see different things are there. So for example, we can see a circular reservoir. You can input certain things over here. So you can input the parameters, and then it will give you the thing you require. So okay, so it says for your invalid material specified, we can go and specify certain grade. Okay, so this is a circular reservoir according to whatever thing that you want. Another thing that we can get is for example a shell, hemispherical shell, for example a dome. We can specify the dimensions. So for example, diameter I want it to be 6 meters, the height I want it to be, for example, 1.5, and then thickness, whatever, fixity, and the material we can specify C40, for example. Putting the loads that you want, apply. Do you want to overwrite the previous data? Yes. So this is going to be your hemispherical shell, or this is going to be your dome. And then trusses as well. You can go for trusses. You can choose whatever type of truss, whatever truss you want, and then you can input the values. Material you can specify which steel. For example, let's say that 355. And then we can click on OK. So we need to keep on adding sections here till this particular window will go. So for example, we can go and choose a section, whatever is the section, for the sake of just showing it. So you will see that it will go. So we need to add a top code, whatever section. Just let's say that we're going to use equal angle section. Let's use, okay, so bottom code. So a lot of things are still bending. I'll just choose any verticals. So whatever verticals are there, diagonals or bracings, burlings, I'm just doing it for the sake of checking the final shape. And then the beams, the connected beams. Let's say that we're going to use I section, and then click on OK. Yeah, no need to. Okay, so this is our modeling of the trusses. The same thing for the RC building frame. You can specify, you can play, like for example, we have number of columns here to be 4 in this direction. So 4 in this direction, I want it to be 6. So number will be increasing to 6. How many in the other direction? So for example, I want it to be 5, so it can be 5. How many stories, distance. We can go and check this particular thing in the coming lectures as well. Anyhow, thank you very much for listening to me in this particular lecture, and then we are going to continue in the coming lectures. Thank you very much.